Okay, let's get started. The first talk this afternoon is Frans Pretorius, Gravitational Wave Observation of Dynamical Strongfield Gravity.
Thank you, and thank the organizers for giving me a chance to talk here. Microphone? Do I? Oh, there. Thank you. Okay. So yeah, I want to thank the organizers for inviting me to talk here. It's a great honor to be here and talking at Stephen Hawking's 75th birthday. You know, academically, he's an inspiration to a lot of us, and as a human being, just as an example, of someone overcoming such obstacles and having living such a positive, strong life. So it's a great honor for me to be here talking at his birthday. So I'm going to talk about gravitational wave observation of dynamical strong field gravity. And in many cases, it's going to sort of be an extension of many of the talks that you heard this morning. So of course, LIGO has opened up the gravitational wave window into the universe. And as Gabby mentioned this morning, there's a tremendous amount of physics and astrophysics that we hope to do with gravitational waves. Black holes, of course, we've seen black holes, neutron stars, populations of objects. Hopefully we'll see some surprises, perhaps cosmic strings, perhaps primordial black holes, who knows. But there's a lot that we hope to discover about the universe over the next few decades with gravitational wave astronomy. I'm just going to focus on just a very small aspect of that, so just looking at black holes, and just a subset of the things that we can do with black holes. In particular, the thing that I'm going to be talking about here is how can we test general relativity in this dynamical strong field regime using gravitational wave observations. And so my talk's going to be perhaps two take-home points that I want to make over the next 30 minutes or so. The first is, I think I've turned it off. Oh, there it is. The main point here is that this first event that they detected is a spectacular piece of data, and I think it's eventually going to be a game changer in being able to rule out alternative theories of gravity or exotic alternatives to compact objects in relativity, such as boson stars, gravistars, traversable wormholes, some of these interesting but exotic objects that people have suggested. And why I say eventually, and this is questions and what has also been brought up in some of the earlier talks, is that at the moment, we really only have templates for these events within general relativity. To really rule out these objects, we need to understand we need to have self-consistent theories where we can model these alternatives and answer what do they say in this regime of mergers. And so I'll sort of try to just show you again the LIGO data, but from the perspective of why this event really is not very good right now. And it's not because of the event, it's because we don't understand alternative theories. So in some sense, in terms of testing relativity in this particular regime, the best we can do now, and that's really actually, it's good, it's not that bad, it's just that we can do specific things about alternatives, but the best we can do is, within general relativity itself, we can look for consistency of the event with the predictions of relativity. What I'll show you is that, and what we've seen before, is that the initial analysis that LIGO does says that these events are consistent with binary black hole mergers in relativity. And in particular, if there is some deviation, either it's sort of a stealth deviation where these are different objects, but they somehow masquerade to look like binary mergers in relativity, or they're very, very subtle differences. These might be Kerr-like objects, they might have hair, there might be something interesting there, but it's going to be subtle. And so if we want to perhaps discover something or really test general relativity strongly, we're going to have to dig very deeply in the data, or perhaps get lucky and get a very, very loud nearby event. So the second part of my talk is sort of a suggestion of how we might be able to dig deeper in the data to get very subtle effects. So within a few years, once LIGO reaches the time sensitivity, we can expect a very rich set of data. If we're lucky, we might have a signal to noise several hundred binary black hole merger, and that would be fantastic. But what's more likely is that we'll have several dozen events like GW15, 09, 14, signal to noises of 20, 30, 40. And so how can we get more out of the data than just looking at these events individually? And what I'm going to suggest is that we can use signal stacking to sort of add up these the signals for multiple events to try to at least get a first glance at perhaps some more interesting things that might be going on, or getting stronger tests of relativity than having to wait for a very, very loud event. And so to illustrate this, there's a sort of a proof of principle. I'm going to go after the next subleading quasi-normal mode in the black hole ring-down signal. In some sense, you want to think of this sort of as a test of the no-hair properties, or it's perhaps more correctly of the final state conjecture that essentially says that if when gravitational collapse happens, or you perturb a black hole, in this case very strongly, you smash two black holes together, in general relativity, the prediction is that it's going to settle down to a unique member of the Kerr family of solutions in vacuum, so uniquely characterized by two numbers. In other words, these things are very, very simple. So the way that we can use this aspect of black holes in relativity to test relativity is if we can measure more about an event than there are fundamental parameters that govern the system. So for a single black hole, there are only two fundamental parameters, the mass and the spin. For a binary, there are going to be two black holes in the binary, and they're the properties of the binary. So if we can get a signal-to-noise, very high signal-to-noise event ratio, in principle, there are more numbers there than what are needed to characterize the event in relativity. So if we can sort of extract independent subsets of the data and try to invert it to reconstruct aspects of the original signal, they better all line up. They better all be consistent if this is black hole mergers in relativity that satisfies this final state conjecture. And so one sort of clean way to go after this is to measure multiple of these so-called quasi-normal ring-down modes of black holes. So if you perturb a Kerr black hole, it rings, it emits gravitational radiation, but with a very particular spectrum of oscillation frequencies. There are infinitely many of these quasi-normal modes, the L and M azimuthal numbers. For each one of them, there's an infinite set of overtone numbers. So there are infinitely many modes with different frequencies, but they all are uniquely determined by the mass and the spin of the black hole. So measuring different modes, you can invert them and obtain independent estimates of the mass and the spin of a black hole, and then the test of relativity would be, are they consistent? So what I'll first do, and this is carrying sort of over sort of the analysis that Bruce did this morning, so he did a very nice sort of back-of-the-envelope physics describing the physics of GW150914, and what I'm going to take it a little step further, and sort of reinterpret that in the context of testing relativity. And I want to argue that we already are getting, I'm calling the zeroth order test, that this event is consistent with these properties of black holes. And then I'll sort of argue how we can also use these assumptions to stack multiple signals and hopefully go after the next subleading multiple mode. Okay, so first, let me just very briefly just say what I mean by the Strongfield regime. So in relativity, it's not easy to describe what the Strongfield regime is, because relativity has no intrinsic scale, so it's not like other particle physics where different interesting things might happen as functions of scales. In relativity, it's the geometric theory of gravity, so in some sense the Strongfield regime is defined as if you have some other aspect of a system, say the mass of an object, is if some measure of curvature is large in some sense relative to some other characteristic scale in the problem. And then in some sense that becomes the Strongfield regime. In the universe, we think there are at least two main sort of places where this is relevant. One is compact objects, so black holes and neutron stars are definitely in the Strongfield regime, outside the horizons of black holes. So I'm sort of focusing on what we might be able to see observationally. And then also the universe as a whole, on scales of the Hubble radius, it becomes Strongfield in this sort of notion of what Strongfield is. So why is that interesting in relativity? Well, it's a nonlinear theory, so interesting things happen in nonlinear theories when you invoke those nonlinearities. And one of the most sort of profound consequences of relativity is you form a horizon. And of course, once you have gravitational collapse in a compact object, of course, things inside things even get much more interesting. But even just the fact that a horizon formed, that space-time changes character, it becomes intrinsically dynamical, that's already a fascinating prediction, even if we ignore things that go on even further inside the horizon. Now, of course, black hole horizons aren't exactly the same as sort of cosmological horizons, but it's sort of, they get to argue that it's a similar regime of strong field as black hole horizons, just do the little thought experiment of to take some matter of arbitrary density, arbitrarily low density, and just start collecting this matter in a sphere. Now we know at some point, it doesn't matter how low the density of that matter is, at some point you'll get to a radius where a black hole will form. And that's of course because relativity has no intrinsic scale. Black hole formation has nothing to do with the density of the matter. It's the way that these things scale in relativity. And so, for example, if you take matter with the average density of the universe today, and you do this little experiment, and you do it in asymptotically flat space, by the time you get to a scale that's roughly the Hubble radius, that will form a black hole. So if we were in asymptotically flat space, we'd be inside a black hole. So of course we're not, but so the only way to avoid us not being inside a black hole is that on global scales, the structure of space-time is very, very different. The topology and the structure of space-time on large scales is different. But in some sense, what the argument is that if you think of strong field gravity as where GR is so different from Newtonian mechanics that horizons can form, then the universe on the Hubble radius, even today, not just at the Big Bang, is strong field gravity. Now with compact object mergers, because this is now going to be a very dynamical situation, and so dynamical strong field gravity, another characteristic is that in these mergers, the luminosity can approach a sizable fraction of the Planck luminosity. So with these binary black hole mergers, it's perhaps 2-3 orders of magnitude away. But the interesting thing about the Planck luminosity, well, first you see here, there's no quantum mechanics here, so there's no h bar in this, but it still seems like this might be a limiting luminosity in some sense in relativity, in the sense that if you try to create or envision a causal process that can emit energy at this luminosity, then either a singularity has to form or a black hole has to form. Okay, so why bother testing this regime of relativity? I've just said it's a scale invariant theory. We have excellent tests of relativity in the solar system, laboratories on Earth, the binary pulsar. And right, okay, if that was the last word, then right, we can test the Schwarzschild metric, where Mercury is, several million Schwarzschild radii away. And that tells us everything about the Schwarzschild space-time. We don't have to go to the horizon. But of course, that, as scientists, I think we want to make sure that actually really is the nature of gravity if relativity is a correct theory outside of quantum scales. On the other hand, we do know that that can't be the entire picture because relativity is fundamentally inconsistent with quantum mechanics. So there has to be some other theory that at a scale introduces changes to GR. So that the usual naive expectations is that should be at the Planck scale. But I guess the firewall proponents have recently argued that actually might not be the case. That there were some arguments resolving this information loss paradox, which were going by the names of the firewall, suggest that there might actually be changes for astrophysical black holes that are induced by quantum effects. So we should be able to test that. I think the existence of dark energy and dark matter should also perhaps make us pause in that we really have the correct description of gravity on those scales. The evidence for those things is largely gravitational. And as I've argued, I think that dark energy being something that's relevant to the larger scales of the universe is a strong gravity phenomena. Dark matter isn't. Dark matter is sort of in the weak field in some sense. But then again, there have been some proposals, and you can argue how much you agree with these or not, where there has been a connection between the cosmological constant and dark matter. Okay. So now, at least on the scales of stellar mass black hole horizons, we can now start testing strong field gravity thanks to these remarkable detections by LIGO. And so for this talk, I'll focus on, I'll do what Bruce did with, sort of recap what he did to explain the aspects of the signal. But at least for now, the most important part of these plots are those 2 or 3 diagrams showing the residuals. So what was done here is sort of the best fit numerical relativity waveform was taken, subtracted from the data, and what's left over is consistent with noise. And so what the LIGO people were able to conclude from that is that after doing that, especially for this first event, which was the loudest, it doesn't support more than a 4% fractional deviation in the waveform from the prediction of relativity based on the fact that the residual is consistent with noise. So that's a pretty strong constraint for the entire waveform. And as I mentioned, though, with the one caveat that if there are some modifications that are larger than that, if there is a general relativity merger waveform that can match the modified theory, so it can masquerade as a GR waveform, then this doesn't cover that. But at least amongst those things, this is a pretty strong constraint. And I forget, that's just taking everything, but if you just think about everything that this is telling us about, it's all the rich physics that we know and love about black holes that were sort of discovered in the 60s and 70s by Stephen and a lot of people sitting in the audience here. So we have this runaway emission due to the runaway in spiral due to gravitational wave emission. There was at least a possibility before we solved the problem in GR that collisions would produce naked singularities, but they don't. We know now that they satisfy the no bifurcation theorems, the area theorem. They merge into a larger black hole. There's a ring down to a Kerr black hole. I think what surprised a lot of people, as Harold mentioned and Pablo in their talks, is how rapid the transition from in spiral to ring down is, and then the fact that this remnant settles down to a unique Kerr black hole. So everything, all of these aspects of black hole physics is sort of folded into this one statement. Okay, so again, if there are deviations from relativity, either they stealth or they're pretty small. So perhaps if you want to now say, well, let's look at some of these exotic alternatives, modified theories of gravity, what would be the best way to try to confront them with the data? And it would be the same way as we're confronting general relativity with the data. We've got the predictions from numerical relativity. We do this residual test, and it's small. So we say, okay, that's some confidence that relativity is correct. But the problem with all alternative theories, and that comes to a question that was asked this morning, is, well, has LIGO applied alternative theory templates to the event? And the answer is no, because there aren't alternative theories where the merger regime has been solved, at least alternative theories which predict significant deviations in the vacuum problem. Like it was also mentioned, like Brans-Dicke theories, for instance, they don't predict deviations in this regime. So this plot, so people in numerical relativity know this plot very well. It's a famous plot by Kip Thorne back in the days when we couldn't solve this problem in relativity, and he was sort of arguing like why this is very important. If we're going to be using match filtering to detect these things, missing all of the stuff that goes on in here, it could be give a very significant hit to the set of systems we might be able to detect. And it's interesting, there was also sort of a debate at the time, okay, let's assume cosmic censorship is satisfied. How complicated is the merger regime? We think this is a nonlinear theory. This is perhaps the most nonlinear event outside of the Big Bang that we could have in the theory. And there was at least some Kip's prejudice, and I would have been on this side as well, would say there's got to be something, some metastable state, some nonlinear mode coupling at the very least that goes on, some interesting signal before it settles down to this ring down. But there was another camp, Alessandro Buonanno, Thibaut Damour, the effective one-body people, that said, no, because you're in such a deep effective potential, even though there's very interesting stuff that might be happening in space-time, it's all swallowed by the black hole. And the signal that you get outside is very, very simple. And the second answer turned out to be correct. But the point here with alternative theories is we don't know. Right? We just don't know what's going on there. And to sort of make this point a little bit more clearly, like why, especially why this event, I say, will be a game changer, is essentially all of the signal to noise is coming from that regime where the question mark is. So we have a tremendous piece of data right in this part of the theory. It's going to have a tremendous amount of discriminating power to constrain theories if we can understand that regime in those theories. So what I'm showing here is the two signals from the Hanford and the Livingston one, overlaid with the best fit numerical relativity waveform, also convolved with the noise spectrum of the detector. So if you look at that little black curve, you can say, like, why is there all this little funny oscillations? It's not inaccuracies in the numerical relativity waveform. It's because it's been filtered with the detector noise. And so we could ask, well, what if the LIGO detectors had a flat spectrum? Like, what would this waveform look like? And that's what it would look like. Right? So the in spiral is actually a very strong part of the signal. Why it's not strong in this initial event is this is too low frequency. It's now getting to the point where the LIGO noise is overwhelming it. But what you can see then is of this infinite wave training principle and this merger signal is really just this final phase of the merger which is giving us the signal in LIGO. So a lot of words in this slide. Let me just sort of, again, just rephrase what I was saying. I think what this event has done is it's sort of thrown down the gauntlet for alternative theories. If you want to say that you're a viable alternative to general relativity, or you're some viable exotic compact object within relativity, and you want to be consistent with the data, it's not good enough anymore to be consistent with solar system data, the binary pulsar, not even sort of the post-Newtonian regime or ring down of objects. You have to explain what happens when two of these exotic objects collide and smash together. And I think once people start solving some of these problems in alternative theories, this piece of data, I think, is going to be a very, very strong piece of data that's going to constrain or rule out some alternatives. Okay, so now let's get to sort of the second part and say, okay, now, unfortunately, we can't say too much about alternative theories, but what can we say about relativity itself? How consistent is the signal with relativity? And as I mentioned before, perhaps the most powerful agnostic test is just, well, let's take the full prediction of relativity, the full waveform, and look at the residual. And yeah, that doesn't support more than a 4%. But of course, and relativity doesn't break apart the signal into things like area theorems or uniqueness theorems or quasinormal modes. But for us to understand these events, it's a very useful way to think about the physics of these events, to break them apart. And in particular, I think one of the cherished properties of black holes that we could go after is is stated by this final state conjecture. And just to sort of say it in rough words, this is basically it's not the uniqueness theorem, it's more than the uniqueness theorem. I'll say in a second why it's more than just the uniqueness theorems. But it's essentially because it's a statement about dynamics. So it's saying if you form a black hole, you collide two black holes, even if you have multiple black holes, in sort of generic situations that might arise in the universe, these things are very, very simple, at least in terms of the parameters that you need to describe in relativity. It's a unique two-parameter family for the final end states, but also dynamical situations, they evolve to those end states. So just for contrast, like sometimes these are called tests of the no-hair theorem, and I often also sort of colloquially say tests of the no-hair theorem, but that's not quite correct because, strictly speaking, the no-hair theorems are statements about the class of stationary black hole solutions that are allowed. So you assume some spacetimes with very particular symmetries. In other words, the ones that are relevant, in particular, there's no gravitational radiation, there's no dynamics. And so if you just had a statement like that, well, there'd be perhaps two main conclusions that you can draw. The first, and even back in those days, this was known in Israel's original paper. In the conclusion, he discusses both of these alternatives, and the one is that these solutions that you found are sets of measure zero. They're artifacts of the symmetries that were imposed to get these stationary solutions. Because we know, in the real universe, the universe isn't stationary. It's not exactly vacuum, even in the vicinity of black holes. So the conditions for the no-hair theorems don't apply in any situation in this universe. So either black hole solutions are irrelevant to gravitational collapse, and then the alternative in GR would be, okay, they all form naked singularities or something like that. But then the other alternative, which turns out to be the case, and this was discovered through many people's work in the 60s and 70s, is that, in a sense, more the Kerr family are dynamical attractors once gravitational collapse happens. So the uniqueness theorems are very important in this because what it says is that the fundamental number of parameters that govern the dynamics of these complicated systems is very, very small. That's sort of where the no-hair theorem's coming in. But essentially, why we can apply them is because it's really a statement about dynamics. So the final state conjecture is including dynamics. It's not just something about stationary solutions. Okay, so again, this is a little bit wordy. So let me just again explain the basic idea. So what this says is, if we prepare a binary system in relative isolation, so of course I just said the universe is never purely vacuum, it's never in real isolation, there's always going to be some perturbation. But in relative isolation, and we let these things orbit for a while, essentially what the theory says is that this full structure of space-time outside the horizons, so this is things that we want to think about of orbits, like these two black holes orbiting around, emitting gravitational waves, all the quasi-normal modes that are excited when they eventually merge, everything about this binary is described to a level of accuracy that's sort of much more than we'll ever be able to test with experiments, is uniquely described by a very small set of numbers. So the curve parameters of the two black holes and the parameters of the orbit, and that's it. So once we know these parameters, we can predict everything to a very high degree of accuracy about the space-time going forwards, and that's because of this, this final state conjecture. On the other hand, we can measure these signals in principle with arbitrary large signal-to-noise ratio, and just in sort of an information theoretic perspective, there could be many, many more numbers needed to describe the signal than there are fundamental parameters that we need in relativity. And so if we have that situation, then in principle we can take independent subsets of this, invert that, and reconstruct the same fundamental parameters for the events. And of course there are caveats here, noise, and there are certain degeneracies, but this is the basic idea. And again, I want to say this goes quite a bit beyond what's been called black hole spectroscopy, which is sort of taking this idea, applying it to single black holes that are perturbed. As I mentioned before, this is what the final state conjecture implies is if you perturb a curved black hole, there is this infinite spectrum of quasi-normal modes, but the frequencies of all of them are known by A and M. But what this says is it goes even further. It says you don't just have to perturb a single black hole and just understand what the frequencies are. If you collide two black holes, all you need to know are the initial conditions of this binary, and it will predict the final mass and spin, all the frequencies of those quasi-normal modes, but on top of that, all the initial amplitudes and phases of those quasi-normal modes, plus any nonlinear phase in between that's there. So everything about the black holes are predicted by a very, very small set of numbers. Okay, so with that in mind, let me sort of go over very quickly because I'm running out of time. But likely Bruce did a very nice job of this, so I can be very quick here. But let me just sort of argue where in this data already, with this notion of testing the final state conjecture, there's already evidence for that here in the signal. In other words, what we're going to do is we're going to try and reconstruct the final mass and spin of the remnant using two independent parts of the data. And the two independent parts are going to be the in-spiral and the post-merger ring down. So I'll skip this first bit because Bruce went over that. And, he said essentially the way that this ramps up gives you the chirp mass, the way that the place where it terminates gives you the final mass, so we can solve for the two masses. Now my new interpretation of this is, okay, now these are systems relativity, so we have to use some knowledge from what we know from simulations. And in this case, only a few % of the rest mass is radiating gravitational waves. So just knowing what the initial masses are, to within a few %, we can estimate the final mass. It's a sum of the masses minus a few %. So there's a bit of uncertainty in that, but just knowing that, we know what the final mass is. Again, the spins are more challenging, as we've heard in several talks today. But luckily, in this case, for this test, these black holes are comparable mass. And it turns out that if they're in comparable mass, so again, you can do the same argument. If you can measure the initial masses and spins of the black holes just prior to merger, the final spin is roughly going to be the sum of the spins of the black hole plus the remnant orbital angular momentum, minus a little bit that's radiated away. But because these are comparable masses, it turns out it doesn't even matter what the spins are. The final spin is dominated by the orbital angular momentum, and this is what this figure from the Caltech-Cornell-CEDA collaboration is showing, is that taking the extreme range of possibilities, anti-symmetrical, or anti-aligned to aligned, the final spin is still aligned with the orbital angular momentum just prior to merger. So it's a very crude estimate, but we can guess that the final spin is, say, 0.7 plus or minus 0.3. So from the in-spiral now, we've got pretty crude estimates, but we've got estimates of the mass and the spin of the remnant. Now we're going to look at this ring down part of the signal. And one thing that Bruce said, well, these quasi-normal modes, they're perturbations of black holes, so it's the linear theory. This was a very nonlinear event, very violent. How can we trust perturbation theory here? And at least in this case, for these comparable black holes, it turns out that rather astonishingly, you can almost from peak amplitude describe the signal as a sum of quasi-normal modes. You have to include several of the higher modes, and you have to include several overtones of the fundamental mode. But even so, about 80 to 90% of this signal is just the leading L equals 2, M equals 2 mode, quasi-normal mode. So yes, there's a lot going on there, but the majority of this decay is L equals 2, M equals 2 mode. So to within the approximation where we throw away the overtones and the higher order modes, which is much better than the accuracy which we get signal here, we can use this decay to measure that quasi-normal mode, invert it, and get estimates of the black hole mass and spin. And this is essentially what LIGO did in one of their papers, and this is the answer that they get. These are sort of the two estimates of the mass normalized to the mass, the two estimates of the spin, and it's consistent with GR. You can see that this is, I think, 90% confidence interval. So it's a very uncertain measurement if you think that this is the infinity of possibilities allowed by relativity. So this is normalized to the maximum range of mass and to the maximum possible mass. So it's a very uncertain estimate, but it's consistent with GR. And I think you better bile my arguments, but I'd say that the only reason we can make this and this makes sense is because of this final state conjecture. So I think this is the zeroth order test. Okay, so how do we go beyond zeroth order? So essentially what we want to do now is we want to add more estimates of the final mass and the spin to this plot. So one way of adding another estimate is let's get the next leading order quasi-normal mode. It's independent from the first one, so we want to then invert that relationship and see is it also consistent with what we got here from the in-spiral and the leading order mode. The one thing that's nice about the higher order quasi-normal modes is that they probe shorter scales. If you go to larger L and M, so the azimuthal numbers, you probe smaller and smaller scales. So the leading order L equals M equals 2 essentially probes scales on the order of the light ring. So if you want to test these firewall hypotheses, like ideally we'd want to go to very, very high L's and M's because they start to probe smaller and smaller scales. The problem, well, at least in GR, there is that these higher L and M's are excited with very low amplitude relative to the leading 2-2 mode. But moreover, they've got much lower quality factors, so they decay much, much more rapidly. And so there are estimates that if you want to go for the next leading quasi-normal mode, say that L equals M equals 3, you might need a signal with 10 times the SNR. So it's SNR 2 to 300 signal to get to directly measure just one next to leading mode. But then as I mentioned, so how do we go after that? Well, yeah, one is just be patient and wait for the 200, 300 SNR event. But if you want to be less patient, let's start to dig into the data as soon as we can. So one thing that I think is more likely is we'll more likely have a handful of moderate SNR events, 20, 30, 40, then we'll have one ridiculously loud one. That might not be the case, but let's assume that we only have a few of these moderate ones. Can we somehow add up all of this data and look for a collective higher order mode? And since I'm probably only got like 2-3 minutes left, I'm going to skip through the details, but I'll just give the basic idea. And the answer is, in this first study, it seems to just be yes, so we can. So what we're going to do is, again, we're assuming that this final state conjecture, so these things all ring down to Kerr black holes. One issue is that the population of events are going to be different. They're all going to be different Kerr black holes. So if we want to say go after the L equals 3 mode, the next sub-leading mode for most cases, they're all going to have different frequencies. So if we're just saying we're just adding up the signals, if they've got different frequencies and they've got different phases, it's going to be incoherent, and we're not going to get any enhancement. So what we have to do is we have to somehow rescale the signals so that we phase align them initially. And that's where sort of, again, the broader side of this final stage conjecture is so crucial in the sense that with these events that have signal to noises of 20, 30, 40 for the entire waveform, most of that's going to come from the in-spiral, so we have very good estimates of the parameters of the two binaries, or fairly decent estimates of the parameters of the binaries, which means we should be able to then predict to a reasonable degree of accuracy, using numerical simulations, what all the initial phases and amplitudes are of the 3-3 modes. So then using the predictions from the in-spirals from all of these different events, we can rescale each one accordingly so that we can phase align the modes, and then we can do the addition. So they're just sort of illustrating with some sample data. This is the 3-3 mode before alignment. After alignment, of course, and this is not real data tinged by noise, so it's of course it's a very clean alignment. And so that just skipping over a lot of details, but then the one issue here is the alignment's not going to be perfect because we're estimating it from data. So there's going to be some what we call parameter estimation noise. And the other issue we have to deal with is when we rescale the signals, we're rescaling the detector noise as well. So we're adding rescaled versions of the detector noise. So it's not, there's some issues here, but that's the basic idea. And so just the result. So this was sort of a Monte Carlo simulation of 100 realizations of 1 year of detections at advanced LIGO sensitivity. And what I'm showing here is the signal-to-noise ratio of the 3-3 mode, first in these orange bins. That's for individual events. So we're taking the loudest event in 1 year of data from a simulated the set of detections by LIGO. And if we say just arbitrarily, let's say signal-to-noise of 5 is the threshold for detection, this says that, so that the majority of realizations don't have a single event that's loud enough where we can get a single event detected. But when we do the stacking, it turns out that there's several reasonably loud events that contribute, and it shifts the distribution over by a factor of 2 to 3. So it's not great, but in something like this, which is marginal to begin with, it goes from being perhaps 30% chance of seeing a single mode to almost 100% chance of seeing a collective 3-3 mode. And of course, this depends very much on what the actual event rates are. But the important thing is that the relative scaling is unaffected. So if we're more lucky, we might even see one event, but then we can stack those and even get an improved detection. And there are a lot of simplifications that we did with this. So not using fully spinning processing binaries, etc. But so this is sort of like a first proof of principle study that I think this is an interesting way to perhaps go after this. I'll skip that. And so again, just to summarize, the way to test relativity with this is we've assumed that this final state conjecture holds for binaries. And so if we do all this rescaling and summing, assuming that, and we don't see a signal when we expect to see something, then something is wrong. So it'll be easy to see if there's something wrong with what we've assumed. It will be less easy to actually try to discover what's going on, assuming that we haven't had any issues with the analysis. Of course, if there's something glaringly wrong, then perhaps the best bet would be to actually just observe that. So with a very, very loud event, but at least with this thing, we'd be able to show consistency. Okay, so to conclude, I'm just sort of just more. Not really summarizing what I've said, but just also thinking, in terms of what we might hope to expect from LIGO, and sort of what motivated the studies, like thinking like what data could be there 5 years from now, and what can we do with this? And so I've sort of organized it into 3 categories. So one is we expect many binary black hole events, perhaps orders of hundreds. So what can we do with such a large population of detections? And I've just given one example with this coherent stacking for the quasi-normal mode, but there are many other things that you might be able to do. So that's related to one of the questions earlier today. You could start figuring out what the progenitors of binary black holes are. Are they dynamically assembled? Are they assembled in the field? Because that will affect the spin distributions of the progenitors. Another very interesting possibility is a so-called the string axiverse, or these scenarios where there are very light scalar fields with Compton wavelengths comparable to the masses of the black holes. And for rotating black holes, there's a superradiant instability where that will extract rotational energy from the black hole. And so if this scenario exists, we shouldn't see any progenitors of very rapidly spinning black holes of that mass. So if after 100 mergers, there's no evidence for significant spins in all of them, that might point to that. The other interesting bit of data is hopefully we'll have one very loud event at least. And I think then we could sort of look for things that surprise us. Firewalls, for instance, there might be something that just pops out of the data that's not explained by relativity. And then another, I think once, at some point, we're going to get very bored with all of these announcements by LIGO of all the black holes that they're detecting. But I think that then the interesting thing, aside from these populations are waiting for the record breakers, are going to be rare events. I'm very interested in eccentric mergers, for various reasons. They're probably very, very rare, but if they're there, they could teach us a lot about, GR or their formation scenarios. We don't expect black holes to form with very large spin, but perhaps we're wrong. If they're near extremal black hole spins, that would be interesting. But at some point, mining the data for some very rare events will be interesting. So I think just looking at a very small subset of what gravitational wave astronomy is going to be, focusing on these binary black holes, I think the future is very exciting. So thank you.
of gravitational collapse motivated by the information loss problem, in which GR is followed all the way down to R equals 2m, but no horizon is formed, and extra gravitational radiation is produced from transitions inside the region, R equal to m. What is the best evidence in any one particular case that we have a horizon? Is it the ratios of the quasi-normal modes, or is it that if there were no horizon, the thing would act as a sink, as an advected accretion?
Yeah, that's a very good question. I think the answer sort of depends on what you think might be sort of replacing the horizon. And if it's something, I'm not quite familiar with the example you're giving, but let's say, for example, fuzzballs.
Good. I wasn't going to mention that word, but we've done it.
But I think, like one problem is if you could give a well-defined theory of the dynamics of these objects or formation and give some effective PDEs, we could simulate it and we could see. But then the best you can do is sort of based on arguments. And like with these fuzzballs, for instance, at least as far as I understand them, the majority of them, it's expected that you only start seeing deviations within some fraction of a string scale or a Planck scale. And I think in those cases, it would be almost impossible to detect any differences. You want deviations that are on the scale of a fraction of the Schwarzschild radius outside. And so I think, like, for example, like with what these leading order quasi-normal modes suggest is that these events are compact at least to within the light ring. Like the leading order quasi-normal mode is associated with the light ring. On the other hand, I think with exotic compact objects like boson stars, you can make boson stars that are more compact than the light ring. The problem is if they don't collapse immediately to form a Kerr black hole, there's going to be violent matter oscillations, and that's not going to produce quasi-normal modes that are consistent with a final Kerr black hole. So if there's an exotic kind of matter that doesn't promptly collapse to a black hole, I think it would be a very glaring signal. So for example, my suspicion of some of these, so there's been some very interesting arguments about, for example, looking at echoes. If there is all they're horizonless objects, so these things called gravistars, or perhaps they are traversable wormholes. And so you can imagine, like, so waves can fall into the horizon, but they can escape, and you might get echoes of the ring down. And that is only true is if these exotic objects, so take two wormholes and you make them collide, if they collapse to a traversable wormhole on the very, very short time scale such that it looks like a Kerr merger. And I think that would be a very difficult thing to have a generic alternative satisfy, that the initial stage relaxes to one of these exotic objects as rapidly as two Kerr black holes relax to a Kerr black hole.
No, I wasn't suggesting trying to prove one of these theories, but rather prove a deviation from GR by not having a horizon. But I think you've answered that.
Yeah.
I think the stacking is a very powerful technique. However, there are a lot of caveats.
Yes.
You are rescaling the data, so you are comparing about the noise. You assume that it's Gaussian and wide, so it would cancel.
Yeah.
But when the rescaling, you are adding up noise from different frequency bands, so it's not clear how that is going to scale.
Yeah.
So I think it's worth trying,
Yeah.
perhaps with simulated signals, injected signals, to see what the histograms look like. I think that would be very interesting. But I think this is the optimistic prediction.
Yes, so I think I did gloss over the caveats a bit, and I'm glad you mentioned this up, because it is probably the most optimistic type answer. But I think like the reason is so that it's not meant to be the end all of analyses. It's sort of saying, okay, if we think there's something interesting in a very weak part of the signal, let's try to go after it and get a glimpse of it. And eventually, we'll get a loud enough detection where conventional means will work. But if we can get a factor of 2, especially for these marginal cases where they're on the verge of detectability after a year of data, I think it's worth exploring. And perhaps it's a factor of 1.5, but even that might be interesting.
Bruce, you had a...
Frans, I wanted to correct 2 things. First of all, you showed a plot of the residuals from the discovery paper. I'd like to read you the caption.
Okay.
Solid lines show a numerical relativity waveform for a system with parameters consistent with those recovered. Does not say best fit.
Okay.
That's important because some people have misinterpreted that statement. And so be careful what you make of those residuals. That's the first comment. The second comment is that when you showed the waveform and you showed that it had that the strain had larger amplitude at low frequency, but that we didn't see that because of noise in the detector. One of your first slides, that one. The words that you used were wrong. The reason why you don't see that amplitude blue signal is because we've applied a bandpass filter to eliminate the low frequency detector noise, but that also eliminates the low frequency gravitational wave signal. So it's the bandpass filter that eliminated that, not the detector noise.
Sorry, thanks for that clarification. Yeah,
okay.
I misspoke.
Apart from that, I liked your talk a lot.
Thank you.
I think we have time just for one more very quick one. Gary.
I have two brief comments. First, in 4 space-time dimensions, you can forget fuzzballs. There are none. The second comment is that you used, if I heard correctly, the words Planck luminosity or something like that.
Yeah.
Now, Planck's constant is nowhere in that formula. The formula is c to the 5th divide g. It's a purely GR maximal luminosity. And I've suggested, and I would suggest to everybody in this room, we call it the Dyson luminosity, because he was the first person to realize its significance.
Thank you for, where I mentioned that there seems to be a limiting luminosity if you do these thought experiments and try to create something. That's Dyson's original work. So thanks for bringing that up.
Okay, I think we need to move on, so let us thank the speaker once more. Thank you.